Welcome to the AIDI Operation Tutorial Series video. This series of videos aims to help machine vision engineers learn how to use AIDI for model training, evaluation, optimization, and other operations. This video will guide you step by step on how to use the AIDI Segment Module. You will learn the detailed steps and usage tips for functions such as importing images, defect labeling, setting training and inference parameters, model evaluation methods, and secondary development integration within this module.
Segment is one of the most commonly used modules in on-site projects. It classifies pixels in an image and outputs information such as the defect area, the length and width of the minimum bounding rectangle, helping operators precisely control defect size and area during inspection. With pixel-level inspect capability, the segment module can accurately identify even tiny defects, such as scratches, dents or cracks, making it ideal for fine appearance inspection tasks, like those shown here. Now let's take a look at the AIDI interface and its main functional areas. Switch mode, change between different labeling modes. For example, defect labeling and ignored area labeling. Label tools. Select different tools for image labeling. For example, circle pen tool and line pen tool. Project. Switch between projects or manage project settings. Modules. Select algorithm modules to build detection solutions. Image list. View and manage imported images. Image management. Import or export images and manage image data. Labels. Add, modify, or delete label classes and assign tags to images or views. Training and inference area. Set model training and inference parameters. Evaluation area. Evaluate model performance after training. Using AIDI typically involves the following steps. Step 1. Create an AIDI project. Step 2. Load the defect images needed for training on site. Step 3. Select an appropriate AIDI algorithm module. Step 4. Label the defects in the images. Step 5. Adjust training parameters and conduct training. Step 6. Run inference on your model. Step 7. Evaluate or optimize your model. If the results are unsatisfactory, go back to Step 5. Adjust parameters or add more images to the training set, and retrain. Once the model meets the desired performance, you can export it to the production site. Through API integration, the model can be embedded into the system software, completing the AI deployment process. This section will introduce the requirements of AIDI for image formats and sizes, and demonstrate how to complete the creation of the project and the import of images. After opening the AIDI software, the first to appear is the Project Management interface. Here we can select the workspace, click Select Folder, and create a new folder on the desktop. Now the local workspace has been established. Subsequent work on site projects can be created within this workspace, which is convenient for site personnel to maintain and manage the projects. Right-click in the workspace and select New Project. You can name the project based on the workstation and the defect type to be inspected, for instance. The exact naming convention can be aligned with the on-site team. In this example, I will name the project after the module. If your image is a regular 2D image, select the normal project. If you need to import other formats or types of images, such as mixed images, 3D images or TIFF images, you can select the corresponding project type. You can also view the user documentation in the Help option of the AIDI menu bar, or consult AIDI's technical personnel to understand how to use this type of project. It is recommended to import PNG and BMP images in the General Image project, and JPG images are not recommended to use. AIDI supports the maximum importable image pixel size of 30,000 × 30,000. If the image exceeds this size, it is recommended to first use other traditional algorithm tools to crop the image to a size within 30,000 × 30,000. Now we are showing the interface after the AIDI segment project is established. Click Import Image in the Image I/O area. You can choose to import a single image or an entire folder. Here we choose to import a single image. Select an image. Press Ctrl+A to select all images and choose Open. Click Confirm. After the image is imported, click the plus button next to Input, and select the Segment Module. This section will introduce the AIDI View function. I will show you how to mask out interference areas, crop large images into smaller ones, and perform normalization operations after importing images of different sizes. Through this function, you can accurately operate images and improve work efficiency. Next, let's see how to operate. Mask out interference areas. For example, if the defects we inspect in the images currently only appear in the upper left corner, and not in the lower right corner, or in case the lower right corner is outside the area of the product to be inspected, such as the background or some interference outside the machine. We can adjust the view so that the lower right corner area is outside our inspection range. Firstly, we click inside the view area, then drag to draw a selection box that defines the inspection region. After selecting the desired area, click Apply. At this point, we can see that the upper left area of the image has been selected within this region, and the model can be trained and inferred here, while the area outside the view will not be trained or inferred by the model. Divide the large image into smaller images. What I will show you next is the function of dividing a large image into smaller ones. If the AIDI image you import is quite large, for example over 5 million pixels, and the size of the defects to be inspected is very small, such as 5 × 5 pixels, then if you use the entire image for model training, you will need to set a very high inspection precision, which requires a very high level of computing power. The image division feature can solve this problem. We usually divide the image into multiple parts, and then let the model learn from them. If the minimum size of the defect to be inspected is 5 × 5 pixels, we usually crop the view to a size of 2000 × 2000 pixels for model training. Below is a demonstration of the cropping method. We click on the view, then click on the divide. We can choose to divide into multiple parts and adjust it to 5 parts, where we can see that one large image is divided into 5 × 5 views for learning. The horizontal and vertical intervals are set to negative values, and we can see that the corresponding positions of each view overlap, which can avoid the same defect being cut into 2 parts by the edge area. After setting the parameters, we click the Divide button, then click Apply. At this point, we can see that each image has been divided into small view regions. View normalization. What I will show you next is how to perform view normalization. Generally speaking, it is recommended that customers use the same camera on the project site to capture images for training within the same project, which can reduce the difficulty of model training and improve the model's performance in recognizing features. However, if it is necessary to use images of different sizes for training, or if multiple cameras and products are to share the same model, we can normalize images of different sizes by setting the view. For example, if the image we import now is 512 × 512, and there are other sizes of images mixed in, such as the largest size being 1024 × 1024, we can set the base on the largest view size. Click on the view, expand the view to 1024 and click Apply. You can see that all areas outside the image range have been filled with black. This way, the software can train with the size of the largest imported image, and fill in black around images that are smaller than this size, ensuring that all images input to the model are of the same size. This video uses a sample project where the entire image is used as the view for training. Image labeling is the foundation for the efficient learning of models. In this section, I will show you how to use software for precise labeling to improve the recognition efficiency of the model. In the Label Management area, we enter the name of the defect to be inspected. For example, NG. After entering, press the Enter key to complete the import of the defect category. Then select the label pen. The mouse wheel can zoom in and out of the image. Below is an introduction to the use of various labeling tools. Circle pen tool. Click the left mouse button and drag to paint. Release the mouse button to complete the annotation. Square pen tool. Annotate in the same way. Line pen tool. Annotates based on points. After clicking the left mouse button to confirm a node, move the mouse and then click the left mouse button to confirm the next node. This annotation tool is suitable for marking linear defects, such as scratches and cracks. Double-click to end the annotation. Square line pen tool. Click the left mouse button and drag to draw nodes, and double-click to end. Pen tool. Suitable for the annotation of polygonal curves. Click to set the starting point. Then move the mouse to draw multiple polyline segments, and double-click to end. Freeform pen tool. Click the left mouse button and drag the mouse. Release the left mouse button to end the annotation. Circle tool. Click and drag to create a circle of the appropriate size, and then click the mouse again to end the annotation. Two intelligent annotation tools are introduced below: the Magic Wand tool and the Quick Label tool. For images with clear boundaries, the Magic Wand tool can quickly isolate the image. The Quick Label tool is recommended when the defect boundary has a certain contrast with the product background. The selection of the defect area is completed by adding and deleting selected areas. For specific usage, please refer to the user documentation in the Help option of the AIDI menu bar. These two tools are not applicable to the current image, and no demonstration will be given here. Circle eraser. When there are multiple labeling errors during the labeling process, the eraser can be used for correction. Edit mode. After selecting the edit mode, we can drag to adjust the labeling area and modify the defect category. After deleting the defect category in the labeling management area, all labeling areas of this category in the image will be deleted. The AIDI 3.3 version introduces a new Smart Label tool, which is based on GPU acceleration technology, and can significantly improve labeling efficiency. Please note that when the tool is enabled for the first time, the system needs to load the model initialization for 1 to 3 minutes. When using the Intelligent Labeling tool, please first click the plus icon on the toolbar to enable the labeling function. Move the mouse to the defect area and click the left mouse button to automatically generate a standard area that closely fits the defect contour. If adjustments need to be made to the labeled area, the delete pen can be used to precisely erase the extra parts. After completing the labeling of a single defect, press Ctrl+S to save the current labeling result. When there are multiple defects in the image, separate labeling operations are required. After labeling the first defect, press Ctrl+S to save. Continue to label the second defect and then press Ctrl+S to save again. After all the areas to be inspected in the image are labeled, press the S key to save the labeling data of the entire image, and the system will automatically jump to the next image to be labeled. Now let's take this image as an example to show you how to label. First, we select the circle pen. The mouse wheel can zoom in and out of the image, and the Alt key plus the left mouse button can drag and adjust the image position. Since the image here is large and the pen is small, we can adjust the pen size by pressing the A and D keys on the keyboard. Or we can input directly here. When labeling, it is best to ensure that the area being labeled is the defect area without any background. The segment module is for learning and classifying pixels. If we mark too many OK areas in the background, they will also be learned as defects, leading to overkill situations. If we mark too few, the model will treat the unmarked NG areas in the image as OK areas to learn, which will result in underkill cases. Therefore, when using the segment module, the labeling should be precise and close to the defect edges. After labeling is complete, press the S key on the keyboard to save, and then move on to the next image. If all the defects we mark are of the same label, we can click the Enable Default Label button, and all the defects marked after that will default to this label.
This section will introduce how to divide the training set to ensure that it contains different types of defects, thus laying a solid foundation for model training. There are two ways to divide the training set. The first is automatic division, and the second is manual division. I will introduce the application scenarios of both automatic and manual division, as well as how to select various types of defect shapes in the training set. Firstly, let me introduce the application scenarios of the two division methods. The automatic division method is suitable for the first time picking images for training after completing defect labeling, with the software automatically randomly selecting, saving manual selection time. The manual division method is usually used during the model optimization phase, where representative images are manually selected to join the training set to enhance the model's learning ability for that type of image.
Below we will demonstrate how to select the training set. After labeling is complete, we click the Training and Inference button, select the training helper, select Split Dataset and click Split. The division ratio appears with the default ratio of 70%, indicating 70% as the training set and 30% as the validation set. In the lower left corner of the interface, we can see that there are currently 10 images, with 0 in the training set and 10 in the validation set. We click Split, and we can see that now the training set consists of 7 images, and the validation set consists of 3 images, which meets the 70% ratio we mentioned earlier. After the training set is divided, we can see that a corner label appears in the upper right corner of the thumbnail in the image list. Red represents the validation set and green represents the training set. Images that have been labeled will be automatically added to the validation set. Just now I showed you the effect of the training set division. If there are some representative defect shapes in the training set that were not included in the training set during automatic division, you can use the manual division feature. Select the image, then right-click to add it to the training set. After the training set division, we need to ensure that the training set in the image contains all typical shapes of the defects. Setting the correct parameters is crucial during the training process. In this section, I will introduce key parameters, such as the number of training epochs, training batch size and incremental training, and demonstrate how to adjust parameters according to different scenarios to optimize the model's performance. Training epochs. Learning all the images in the training set once is called one epoch, with the default being 400 epochs. In simple scenarios, we can choose 400 epochs. If the defects on the site are more complex and there are more defect shapes, we can appropriately increase the number of training epochs to improve the model's performance. It is recommended to increase by 100 each time. The number of epochs commonly used on the project site is 1,200. Batch size. When the model is trained, it will merge 4 images into a data packet and input it to the GPU for training. We can appropriately increase the training batch size to shorten the model training time and improve the model's recognition effectiveness. However, after increasing the training batch size, the amount of data input to the GPU will increase, which may result in insufficient GPU memory. When insufficient GPU memory occurs, you can reduce the training batch size accordingly. Normal train. Relearning all the images in the training set is called regular training. Incremental train. After we have completed the training of a model, if there are 2 to 3 new defect images on the site, and we want to add these defects to the training set for learning, we can choose incremental training, keep other parameters unchanged and click to train. This training mode supports learning only the new content, without having to start training from scratch every time, significantly reducing the model iteration time. The commonly used training mode on the site is normal train. which is conducive to improving the model's performance. Precision setting. Auto mode. The model will choose an appropriate precision level, based on our view size and the size of the defects in the view, and then train the model accordingly. Manual mode. This method is to manually set an appropriate precision level and then train the model.
Now I will introduce the calculation method for precision levels. With the precision level set, the short side of the image will be scaled to base side times precision level. In Segment Module, the base side is 256. For example, if the current view is 512 times 512 in size, the precision level is set to 1. The short side of the image 512 will be scaled down to 256 times 1, with the long side scaled proportionally, resulting in the scaled image size of 256 times 256. When the image size for model training is small, the training speed of the model will be faster. However, if the defects are particularly small after scaling by the precision level, it may lead to underkill cases in the model.
For instance, if a 5 x 5 pixel small defect appears in a 512 x 512 pixel image, and the precision level is set to 1, the defect will also shrink to half the size, becoming 2.5 x 2.5 pixels. The software can identify defects as small as 3 x 3 pixels, but to strictly control risks and meet the demand for higher recognition rates, it is recommended to ensure the minimum defect size is 5 x 5 pixels. Therefore, if there are particularly small defects in the image, we can increase the precision level, for example, to 2. Then the short side of the image will be scaled down to 256 x 2. With the long side scaled proportionally, which means our current view has not been scaled at all, so it's fixed at 512 x 512. The maximum precision level that can be set is 32. It's recommended to set the level based on the view's short side divided by 256 as the upper limit. Currently, a view size is 512 x 512. And the recommended precision level is 2, to ensure the model can identify defects of 5 x 5 size. If smaller defects appear, such as 1 x 1 or 2 x 2, it is recommended to optimize the optical scheme and increase the image resolution, rather than increasing the precision level again. Next, I will introduce the geometric augmentation parameters. We can hover the mouse over the information icon on the right to view the effect diagrams of vertical flip, horizontal flip, vertical rotation and center rotation. Slight rotation. In addition to seeing the effect of rotation, clicking the gear icon can also see the effect of field enhancement. The angle range of -5 degrees to 5 degrees represents the range of mild rotation of the image, with a rotation interval of 1 indicating that the image rotates 1 degree each time. This means that within the range of -5 degrees to 5 degrees, the image randomly rotates 10 times to cover all rotation angles. For example, during the first round of training, the image may rotate 5 degrees, and during the second round of training, the image may rotate -2 degrees. Shift 0.01 represents that the image will be translated within a range of 1% of its own size, as shown in the figure. For a 512 x 512 image, 1% is 5 pixels, so the image will be moving 5 pixels left, right, up, and down. Scale. The image will undergo a transformation of magnification or reduction, and we can click the information icon to see the effect. In addition, the training parameters also include 2 image augmentation parameters. Illumination augmentation range enhances the brightness and contrast of the image through an algorithm. Contrast augmentation range improves image contrast by traditional algorithms. If a similar situation appears on the image, we can enable these parameters to increase the diversity of training samples. If it does not appear, do not enable these parameters. In the current case, there is no similar situation, so we can turn off all these parameters. This case is relatively simple. so we can change the number of training epochs to 400. After adjusting the training parameters, click the Training button. You can find the Training button above the parameters, or on the right side of the module name next to the head icon. After clicking the Training button, we can see the training progress bar in the upper right corner, which will display the remaining time, the serial number of the equipment currently in use, the current iteration round, and other detailed information, such as the real training precision and the actual total iterations. If we want to terminate the training early, we can click the Stop button. It is not recommended to terminate the training prematurely during the model training process, as this may lead to poor training performance. However, if we need to change the training parameters during the model training process, we can click the Stop button, make the changes, and then click the Training button again to restart the training. After the model training is completed, it is very important to know how to view the training performance and optimize the model. In this section, I will show you how to judge the overall performance of the model and optimize it by checking the evaluation interface, setting inference parameters, and other methods. After the training is completed, we can see that the colored areas in the image represent the model's inspection results, while the green area is the manually labeled effect. We can switch the display mode by pressing the spacebar. We can judge the performance of the model by checking the inspection results of the images in the validation set. The red triangle symbol represents the image in the validation set. It can be clearly seen that there is an underkill situation in this image. When there is underkill in the model, we can label the unrecognizable defects, and then right-click the mouse to add the image to the training set for the model to retrain. Inference parameter. Inference modes are divided into 3 types: Quick Start, Fast Inference, and High Precision. Quick Start mode indicates that the model will start up quickly. In this mode, after we click on Inference, the model loads onto the GPU at an especially fast pace, but the inference speed will be slightly slower. In Fast Inference mode, the time taken to load the model for the first time will be longer, possibly taking several tens of milliseconds. At this point, the model is not stuck, but is in the process of loading. However, once the model is successfully loaded, the inference speed in this mode is the fastest. The High Precision mode has a slightly slower model loading speed, but a higher precision level for inference. Now let me demonstrate. We select Quick Start, then click on Inference, and we can see that the average time for a single image is 25.34 milliseconds. If we select Fast Inference, the average single image inference time is 2.18 milliseconds. If we select High Precision, the single image inference time is 11.68 milliseconds. A better GPU speeds up training and cuts down inference time. Fast inference is the fastest, but it may result in some loss of accuracy. Therefore, the High Precision mode is generally used on-site. If the High Precision mode cannot meet the on-site requirements, we can try using the Fast Inference mode. Characteristic threshold filtering. After we enable the filtering option, we can filter by defect area short side and long side. For example, in this image, if we select the View mode, we can see that the defect area in the test results is 3112. After setting the area filtering value to 30 to 100 and clicking the Inference button, the image is reclassified as OK. Through similar filtering methods, we can control some minor defects on site, and scattered points that pass the inspection in the image. In the evaluation interface, we can see the recall rate and precision of the model. Below we can see the confusion matrix. We select region level and quality matrix. The vertical table header represents the ground truth, such as this row indicating 10 NG regions manually labeled. The horizontal table header represents the model predicted results. Any area not manually labeled or predicted by the model as NG is considered background. The confusion matrix reveals one underkill case. The model correctly identified 9 manually labeled NG regions, but misclassified one as background. We can click on the number 1 to quickly filter out this image. Through this type of filtering in the confusion matrix, we can quickly locate which images are under or overkill and then optimize the model. In the model details, we can see the total training time of the model and the single view inference time. This time can be used to evaluate whether the model can meet the on-site requirements. When estimating the model inference time on-site, it is recommended to add 20% to 30% more time to the average single image test time, as on-site machines usually run other software, which may occupy the computer's running resources. In the image list area, we can also perform other function filters, such as name search training set, validation set, labeled, predicted, and images labeled as OK. For example, if we filter the images in the training set, we can see that there are 8 images in the training set. If we want to filter images not in the training set, we can click to switch to different, and we can see that 2 images are filtered out. Now that we have added the underkilled image to the training set, we can retrain and check the result. As can be seen, the images after training do not show any inspection errors. After completing the model training, we need to export the model for use on site. This section will show you how to export the trained model. We click on the Model option in the upper menu bar of the software. Select the Export Model button, choose a directory, and export the current model. This is the model file we export for on-site use. In the Model option, you can also export sample code and projects. By clicking on Model and Sample Code Export, you can export the project, set the language, choose a directory, and then click Export. We can see that this is the exported project file, which includes sample code, sample images, and model files. The Segment Module is a pixel-level defect recognition tool that excels inspecting fine defects in complex scenes, such as scratches, dents, and cracks. The accuracy of the labels sets the upper limit for the model's performance, so precise labeling can significantly improve the model's results. When labeling, we should try to fit the defect contour and avoid over or under labeling. The confusion matrix is a common tool for model evaluation. In the confusion matrix, we can quickly filter out overkill and underkill images, which is convenient for on-site model optimization. However, this feature can only filter out manually labeled image results, and unlabeled images cannot be viewed in the confusion matrix. If there are underkill cases on site, you need to label the actual defect area normally. Do not label non-defect areas, and then add the image to the training set for retraining. Thank you for watching. For more tips and resources, we invite you to explore the detailed documentation in the software's help menu, or visit the Acros Technology official website.